Hey everyone, thank you for attending this talk. I'm Salva, a computer science undergrad at TU Darmstadt, Germany. I have Peruvian background and I'm very happy to attend this LatinX and AI workshop. The work I present today is a result of an ongoing collaboration with Ben Birkin and Arthur Dubrovsky from Carnegie Mellon's Autumn Lab. It all started during my summer internship and I'm super excited about presenting some of the work we've done since then. We will study the problem of misspecified weak supervision models in this presentation. First, some background on and motivation for weak supervision. As you probably know, modern supervised machine learning approaches such as deep learning require lots of label data. For instance, to train a modern image classification model, you would usually require millions of labeled images, such as from the popular ImageNet dataset that consists of 14 million labeled images. Now, the usual process is to hand label the required data point by point, sometimes supported by active learning. However, manual annotation is expensive, since often domain expertise is needed. It's also slow, repetitive, dull, and static, and can also be noisy due to uncertainty or disagreement between the labelers involved, or simply due to labeling mistakes. All in all, hand labeling data point by point is a substantial bottleneck for deploying machine learning to new applications and domains. A promising alternative to this is the recently proposed data programming paradigm. Here, a domain expert can encode their knowledge into multiple labeling functions. These are based on noisy label sources such as domain heuristics, pre-trained classifiers, or knowledge bases. Our running example in this talk will be a sentiment classification application on text documents. You can think of classifying positive from a negative sentiment in a movie review. The used heuristics are keyword detector functions that vote when a term appears in a document and abstain otherwise. In the slides, two such heuristics are shown, like the first one that labels for the positive sentiment whenever recommends appears in a text. With such a set of heuristics, we can learn a generative model over the functions and the latent true label that we aim to estimate. We also call this model a label model. Our goal is to produce soft labels that we can use in a final step to train any downstream machine learning model without hand labeling of the data. A basic modeling step to achieve this is to model the labeling accuracy of each of the labeling functions. You may have been wondering what these rectangles in the graph are. These are factors, simply functions that relate the random variables to each other. In addition, the functions may have complex dependencies to each other, such as the one shown on the slide, where the second is fixing the less precise vote of the first whenever the words wouldn't recommend appear in the text. We model these as factors too. Before continuing, it's worth looking at some more example dependencies that we used in the IMDb movie review dataset so that you get a better sense of them. I'll just quickly note that we extend the data programming framework by dependencies that we call bolstering, priority, and negated. For instance, we can model a bolstering dependency between a labeling function voting when best appears in a document and another one that votes when the token great occurs as well. Or we could model a priority dependency between the terms original and bad, that we read as whenever original and bad coincide in a text, we give priority to the negative vote of bad. This makes sense since bad is a pretty strong signal of negative sentiment, whereas original is likely a far less accurate signal for the positive sentiment. The natural mathematical formulation for all these types of dependencies can be found in our appendix. Now, specifying the correct dependency structure is hard though. That's why much of the related work and popular libraries simply ignore the modeling dependencies. That just means that they only model accuracy factors. The question that you may ask is, what effects does it have to model an incorrect structure? That is, what happens if we misspecify our model? The implications from this on downstream performance have not been researched in detail, though. Our work, therefore, is the first step towards a better understanding of the trade-offs due to misspecified models. Based on novel theoretical bounds on the modeling error and the model misspecification, we empirically show that this error can be quite substantial, even when modeling a seemingly sensible structure. Starting with a brief look into the bounds that we found, we compare here two label models with different structures. The first model A is a so-called independent model that only models accuracy factors, while the second model B is more complex and models any higher order dependencies as the ones you saw in the previous table. We do not assume any of the two to be the true one yet. We bound the generalization risk of the downstream model under a misspecified label model. The interesting quantities here are the second and the third one of the inequality on the slide. The second one being denoting the error between the estimated accuracy parameters of the misspecified model versus the true accuracy parameters of the true model. If we assume that an independent model that only models accuracies is the true one, we can interpret the quantity on the right as the excess parameters corresponding to the misspecified dependencies, which are those that are not part of the true model. If we assume that the true model has dependencies, we can interpret the quantity on the right as the magnitude of the dependencies that the independent model failed to model. The presented bounds extend to more general cases, such as where the misspecified model got some dependencies right, but others wrong. Going over to our experiments, we use here the IMDb movie review dataset as well as the bias and bias dataset. On the slides at the end, you can see the dependencies from before, which are for the IMDb dataset. And we added now a last column called factor value. That's our measure of the true dependency strength, where higher is stronger. Only for this purpose, we use the true labels that usually won't be available, but which we can use for this or for the purpose of computing a proxy of the true strength of the dependencies. In this experiment now on the slide, we plot the number of strongest dependencies used in model B versus the change in downstream performance with respect to the baseline model A. What we observe is that a marginal boost in performance when modeling the strongest one or three dependencies of each factor type. However, when modeling more than that, we find our main takeaway that modeling more than a handful of dependencies significantly worsens downstream performance by up to 4 AUC points here, as compared to simply ignoring them. And in addition, the performance worsens further as we model more, slightly weaker dependencies. Again, we reiterate that these additional dependencies semantically make sense, as you can see in the table. We also observed similar effects for our second bias and bias experiment. And in fact, we can observe that modeling dependencies always has a worse performance than ignoring them. And we also observe a more drastic loss in performance. We hypothesize that the performance loss is due to the true model being close to the conditional independent case, or due to the more complex model with dependencies being too sample inefficient. This will be the focus of our future work, as well as fine-tuning the theoretical bounds. We can conclude, though, that the independent model is a reasonable baseline for practitioners. Thank you. This was all from my side.